Okay, so I just want to finish quickly what I was saying last time about syntactic parameters. And so I gave various examples regarding the structure that one can see in the data that are available about syntactic parameters. And of course, from what one can see through the analyzing the data, it's clear that there are lots of relations between what linguists have classified as possible binary variable describing different structures of syntax across different languages. And these, one can, in principle, construct independent variables, for example, by this type of low-dimensional, sort of reasonably faithful low-dimensional embedding of the data. But then if you introduce variables that don't have any immediate meaning or linguistic description, become more difficult to understand what you're describing. So there are other aspects also that one should take into consideration about syntactic parameters. And one of them is the fact that they're also dynamical variables that have been changing over time in various languages. So one can think of how to describe them as dynamical variables. For example, one knows that change in language often comes from interactions between languages. And so one type of somewhat rough basic model that one can build about how syntactic parameters behave is to think of them as some kind of a spin glass system where each language is a node and have its own set of spins that are the positions of the various parameters. And there's interaction between them. If you have like a large bilingual population, so the interaction is roughly proportional to the amount of bilingualism. So if you have a large bilingual population, there's a lot more interaction between these languages. And it tends to be the case that, constructions that are possible in one language but not possible in another one will tend to be adopted if you have a large population that simultaneously speaks two languages. And on the other hand, if this were, so this is another case where you see that if these were all independent variables, then the dynamics of such a model would naturally lead you to an equilibrium state where all the parameters are activated in the sense that constructions are not possible tend to become possible. So everything tend to flip towards the equilibrium where all the spins are aligned in the up position. But this is not what happens. You have languages that maintain a fair amount of diversity in the position of the respective syntactic parameters. And this is again an indication that there are relations between parameters. So the way you should think about, I'm not gonna give the details. I mean, I put a couple of things on the webpage, but you can think of the dynamics instead of having the usual spin glass models of the Hamiltonian is proportional to the interaction of the two spins, so it tends to make them align. You can think that there are additional like Lagrange multipliers that are describing the relations between the parameters. The fact that if you try to flip one of them, this would force several other ones to flip that might and if you try to make small toy models with like small sets of parameters for which it is known what the relations are, then you see that you can make your model flow to equilibria that are not like all the parameters agree. So this is again reflects again the fact that the relations are very highly structured between these kind of parameters. And also, if one thinks of phylogenetic trees of language families and try to model again, the evolution of syntactic parameters as a kind of Markov model on the tree, one can see the discrepancy from that hypothesis, which again is measuring the fact that these are not independent, identically distributed variables. You can also see, in the structure of the data that if you compare the distribution of syntactic parameters across different languages, and you use the kind of methods like persistent topology that look for structures in the data, you see that you have additional structure with respect to the tree, or the phylogenetic tree roughly correlates really well with the persistent connected components. So how things cluster together, they will give you the basic tree structure. But then you find that there are like a non-trivial first homology, and in some cases non-trivial second homology. And some of these things are actually identifiable with things that linguists understand. For example, you find that when you analyze the data of the syntactic parameters of the Indo-European languages, there is one prominent first homology generator in the persistent homology, which basically means that languages that are down several different subtrees of the Indo-European languages have actually non-trivial interaction across these different subtrees. If you look at what other languages involved, you'll find that it's a loop that involves some of the Slavic languages, some of the Hellenic languages, and some of the old Germanic languages like Gothic. And of course, this can be traced to the fact that there were texts, especially around translations of the Bible, that were syntactic constructions from some of them were adopted into other languages at that time. And so there are these kind of loops, but not all of them can be, not all the ones that you see in the data can be identified with something that historical linguists already knew about. Some of them might be noise in the data, but there's evidence that some of the interaction between historically happened across languages is reflected in something more than the evolution along trees. So there's a lot of structure in there, but this means that if one wants to try to model, use the information from syntactic parameters to actually pin down the externalization of the free symmetric merge structures that we have been modeling before, this does require a somewhat better understanding at this point of how to model the space of syntactic parameters, for which it's the kind of data or the kind of coordinates that are usually adopted is maybe not the best form, because again, one can come up with hundreds of these coordinates, and in a sense one is trying to visualize whatever is the space that describe the constraints on actual possible languages as an embedded submanifold of some very large space of binary parameters. And the thing is that to some extent, this very large space of binary parameters should be somewhat arbitrary. And the point that matters is the actual manifold that's embedded in there. And I mentioned this last time, but when historically in mathematics, we went from thinking of manifolds as being certain subsets of Euclidean spaces to think of manifolds as abstract objects and embeddings as something that's accidental and shouldn't be part of the structure. And so I think there is a step. So this is in a sense part of what needs to be done is to move from this perspective of trying to find a large space of binary coordinates into which to describe the locus of actual syntactic variation across languages, to something that would be like an intrinsic description of this as a manifold, not as an embedded manifold. And that would actually give like a much better description of the externalization. So there's kind of ideas. I will not discuss it further now, but if I have time towards the end of the class, I might come back to just describe some general ideas about how one can try to approach this question. And there's another part of this question which is very important, which is what is the dynamics that takes care of setting these parameters when we learn a language. It's the idea behind this model is that the examples that, so there is like this universal internal calculator of syntax, which is common to everybody and is prior to the actual learning of one particular language, but then the explicit examples that one is exposed to of a particular language in the language learning process as a child will set the parameters in a certain way rather than another, and this will filter out the structures that are compatible with that and eliminate the ones that are not. And so one wants like a good description of what is the dynamical system that, given examples, will actually set the parameters one way or another and then establish the correct filters on the remaining structure.
So, is there an estimate for the dimension of this matrix?
Yes, so I mentioned it last time, that on the basis of the data that are available, one can get back for a moment. That, I mean, if on the basis of, here we are. On the basis of the data that are available, which is a few hundreds, I mean, combining these databases, it's about 100 for the SSWL and then about 80 something for the other database. The actual dimension is much smaller, so it should, so obviously it differs because you're looking at much, but it means that at least it drops down to a few tens rather than a few hundreds. That's the so given that the data are what they are, in the sense that they're not they cover only a part of the actual languages and only whatever the parameters that have been used. So far, this is probably a rough approximation, but it just means that the order of magnitude should really not be something that is some hundreds of dimension large. And so, but one point that's useful with respect to this new model of generative syntax that I described is that in earlier models that were based on formal languages, the idea was that this process of parameter setting was aimed at learning a grammar that would produce one particular language as opposed to another. So on the basis of example, you would have to have some kind of, say, dynamical system in a space that parameterizes the possible grammars that would converge to a particular grammar as your, fixed point of the dynamics, and that would be the learned, production of the actual language. And this had actual problems because there are a few results of Beirut and Yogi from several years ago that if you try to do this, there are some non-learnability issues. So there are cases where your dynamics doesn't actually converge to a target grammar. So there are target grammars that are not learnable on the basis of example, and this creates a problem of how this language learning process works. But in this picture, with this model of generative syntax, you don't have to learn the generative grammar. The generative grammar is common to all languages. It's this underlying mechanism that freely generates all possible structures. What you have to learn is the filters that tell you which structures are okay or not once they are already generated. So it's like learning constraints. It's not learning the generative mechanism. And this actually makes it better from the point of view of trying to have construct some kind of dynamical system that will learn the constraints. So, I mean, this is again something that at this stage is still in progress, but one of the goals would be to actually show that these problems of non-learnability that come up if you're trying to learn a formal language grammar will be bypassed by just having to learn constraints that cut down the space of the structures that are already generated by a common generative process. So, okay, so so for the moment, everything that I want to say about this problem of parameter setting and of cutting down the space to the appropriate externalization. as I said, if I have time, I might return to that a bit later. But the actual next thing that I want to discuss is just, I just want to briefly do a comparison between this most recent model that I've been describing and the earlier versions of the minimalist model and minimalist grammar. And the thing that I want to just sort of emphasize is the fact that if we try to give a similar kind of description in terms of Hopf algebras and the same properties that we use to describe the generative process in this most recent version of minimalism, it gets much more complicated to try to model it in that form, the earlier version of minimalism. And this, in a sense, is like in a sense, the main advantages of this new formulation are exactly that it decouples several problems so that each one of them by itself has a more straightforward and better functioning mathematical formulation and can be treated on its own. And then these things are combined, whereas the original version, which was used for several years, and it tries to combine like all of these issues that I've been talking about, including the externalization and the generative process, into a single step. And then what I'm going to try to show is that if you try to do the same kind of modeling, the fact that everything happens at once in a single step makes everything a lot more complicated. So this is based on the second paper that we wrote. We sort of did this discussion. And so there's, again, this older version of minimalism exists in various slightly different forms because it started being developed in Chomsky's book on the minimalist model in the early 90s. And then it basically continued to be like the main model for generative linguistics until this past 10 years, where this more recent model kind of took over. So I'm gonna just focus on one particular formulation, which is due to Stabler, and because it's the one that was better suitable for computational implementations and is a bit more rigorously formulated than the previous steps that were sort of in the making. But we'll see that even though this one is pretty clearly described in the various computational steps, the actual mathematical structures end up being a lot more complicated than the one that we've seen before. So I did talk a bit about this older formulation of minimalism earlier on when I was doing the various the overview of the different historical steps in generative linguistics. So I'm just kind of going back to that now. So there are some main differences, and one of them is that the internal and external merge are just independently defined as two operations. They're not built to be part of a single kind of operations like we've seen before. And they're just separately defined as two different operations. They are defined directly on planar trees in the sense that everything is already after this externalization to the planar structure of one particular chosen language. So there is a minimalist grammar for each different language in this model rather than a single one for common to all of them. And the operations that are performed, the external and internal merge, have particular domains of applicability. So they're not just freely generating structure. They can only be applied when certain matching labels on various parts of the structure can be identified that can be used for doing this operation. So in a sense, this what this takes care of is what we had seen before, for example, with this. So in the newer version, we have this, generate all the syntactic objects, and then you check for certain things which are still language independent, like the existence of a head function, the structure of head and complement and specifier, the matching of theta roles, and all of these things. And those are already like filters on structures that are already formed that will eliminate those for which this structure doesn't hold together well. Here, it's built into the generative process in the sense that, for example, if you want to have the matching of certain theta roles, they have to be built into the labels of the structure, and you can perform a certain operation or merge only if you have matching labels, which correspond to checking that the theta roles are combined correctly. But you don't do it after as a filter. You just do it while by identifying domains on which the operation can happen. And also, instead of this idea that you build your structure by assembling various material available in a certain workspace, in this older version of minimalism, you just work with trees. So you never consider forests. So your operations should always like take a tree and give you another tree. And so this, as we'll see, while workspaces have a very natural and simple of algebra structure, which is just where the product is just putting things together into a workspace. When you're trying to only work with trees, the product and co-product now, you're forced to stack always things together into a tree. And so that we'll see there is a natural Hopf algebra that only uses trees, that it never uses forests, which is the Loday-Ronco Hopf algebra. But this has a structure which is a lot more complicated than the Hopf algebra of forests and that we've seen before. And this will have a consequence that we're going to lose some of the structures that Hopf algebra had, which have some structure that we have seen have a linguistic meaning. So you think that we lose the representation of certain aspects that were possible because of the nicer properties of the Hopf algebra in that mode. Okay, so the punchline in terms of the mathematical structure here is that the internal and external merge will also here correspond to certain algebraic structures that are describable in terms of the Hopf algebra. But no, they are of a kind of different nature. One of them is a sort of quotient construction, so this comes actually from the fact that you have these domains to keep track of. One of them is an associated sort of kind of quotient structure, but because your Hopf algebra here is non-commutative, it's not an actual quotient because you don't actually have all that many two-sided ideals. But it's something that replaces the notion of quotient for non-commutative Hopf algebras. And on the other hand, the external merge determines a different kind of algebraic structure, which is something that goes under this term of operated algebra. So let me just try to get a little bit more into how this works. Well, so here we are working with planar binary rooted trees. And as I said, only with trees, not with forests. And moreover, in this version, not only the leaves are labeled, but the internal vertices are also labeled. And this is where you keep track where something is like a verb phrase or a noun phrase by labeling correspondingly the internal vertices. And you also carry some labels around that are used to keep track of the theta roles. So something will be marked, for example, as a verb, but it will also be marked as something that is looking for a noun or looking for more than one noun, like no, give something to someone. No, so you attach labels to your that keep track of this kind of structure. Okay. Okay, so you have a kind of set of labels for the vertices, which are not just for the leaves. So there's one operation that, of course, you wanna be using at some point in structure, which is this grafting operation that takes two trees and graft them together to a common root, which will be the one that is used to do the merge operation. And here, no, this is both non-associative and non-commutative because the trees are planar. And also, you have one such operation for each possible leaf that you can attach to for each possible label that you can attach to the new root that you form of these trees. So this come with a label attached. And so there's a couple of other operations that, in terms of notation, are useful for describing what the algebra structure involved in planar planar binary rooted trees is, and they usually go. So they're usually denoted with this terminology. I mean, the name is kind of not so, I think, helpful in understanding what this means. So we call them S under T and S over T. But you should think of them this way, like you have a tree S. And I mean, this notation is actually good to remember what this is doing. So you have a tree S, you keep it by the root, and then you slide down the tree T along its right side until you get to the root, and then you attach it. Okay? And here you again hang your S, and you slide down T on the right side until you get to the bottom, and then you attach it down there. So you graph the root of T to the rightmost leaf, and here you graph the root of T to the leftmost leaf. Okay. And of course, this operation is just the combination of these two, where S is simply the single non-loop vertex. And also, because they're planar trees, there's always a unique way of writing your tree as this operation to like a left part and a right part of that tree. Okay, so the construct a Hopf algebra. So first of all, we're going to take what the underlying vector space is. So you take the vector space that is spanned by the planar binary rooted trees with k internal vertices, so k plus 1 leaves. And the dimension of this space can be computed. The sort of combinatorial includes how many such trees there are, and of course you have a choice of the labels for all the vertices. So you have these sort of internal vertices. So you have this additional counting, and you grade it by the number of internal vertices. So it means that in degree 0 you have a single leaf with. Sorry, yeah. So you have a let's say individual. It's a single leaf with k plus 1, so k plus 1 leaves also. And yes, so this grafting operation is compatible with the degrees in this way, that it attaches one new root and two. Okay, so this is just the underlying vector space. And now the problem comes with the fact that you want to define a product and coproduct that satisfy all the Hopf algebra compatibility relations. So they have to be associative for the product, co-associative for the coproduct. They have to be compatible with coproduct, and coproduct are compatible with each other, and there has to be an antipode that is relating the two. And this gets complicated because now, as I said, you have to like stack things together to always form a tree. And there is one way to do this that gets all the compatibility to work. And so if I write down the formula directly like this, it's not very clear to see what it means, in the sense that here it is defined inductively what the product is, because you can always write a tree by splitting it as its left part and the right part, which are of lower degree. So you kind of define it inductively on the lower degree parts, and then you assemble it for the whole tree. And similar to the co-product is defined inductively over degrees. So it's not easy to, but I'm going to just tell you graphically, what they represent in a moment, and then it's much easier to understand what is going on. But anyway, this is the recursive formula, and the antipode can be defined recursively in the usual way, because this is again graded and connected. But so to see what product and co-product mean, it's easier to actually write it down in a graphical form. So what the co-product does, it looks at each of the leaves and the path from that leaf to the root. Well, of course, the trees are upside down, but I mean, here if you think you just go, and then so for example here I'm looking at the third leaf, and I'm looking at the path down there. And then I use this path to split the tree into two parts. So I kind of double that path, and one goes to one tree and the other goes to the other tree. And so I get a pair of trees. So the co-product is taking the sum over all the possible ways in which, so I will have one of them for each leaf. And each of these terms get me, plus the part where I just have the tree itself without any modification on one side or the other. Okay, and what about the product? So the product, now you have to take two trees and combine them into a single tree. So of course, the idea would be that you graft one of the trees into the other. But of course, you have a choice of how you do that. And moreover, you want this to be compatible with how you decompose them here. And so it turns out that you want, in some sense, to use the same idea of using paths from the leaves to the root, also in the product, so that the compatibility will be easier to hold. But okay, now you can say the only way that I can combine two trees together so that I don't have to make any choices except keeping track of the planar structure is to have something to plug into each of the leaves of this. So I take the first tree and I want to plug it into the second tree, but instead of just plugging it somewhere, I want to split it into parts so that I have something to plug into each of the leaves on the other side. And so I split it again by paths from the leaf to the root, like I'm doing here. But now I have to do it the right number of times, because there may be fewer leaves here than there are things to plug it into the other side. So I need to allow trivial paths somewhere that I can use to plug in whatever is left. So for example, I can decompose like this. So I choose this path from this leaf to the root. But now I want to produce 4 pieces because the other tree that I want to plug it into has four leaves. And normally I would just get 2 parts, but I just split it. For example, here I plug in one trivial path that doesn't branch anywhere, and here I also make another. So I make all the possible cuts, possibly multiple cuts of my tree along these paths, and then I distribute it over the other tree. And it turns out that if I do this operation, it is indeed compatible with the coproduct in this form. So this is an example where, unlike the Hopf algebra of forests that I was describing before, the coproduct is actually a somewhat simpler structure than the product. But both of them are, so the product now is clearly non-commutative. And the fact that the product is non-commutative is kind of, so let me flip it the other way around for the way the trees look like. So the coproduct looks like this and the product looks like this. It will kind of be. The fact that the product is so manifestly non-commutative the non-commutativity of the Hopf algebra immediately makes you lose some property. One of the properties that you lose is the fact that the Hopf algebra is dual to a group. And so, and also in particular, you lose the Lie algebra that's associated to that group, which is this insertion Lie algebra that we use, which we have seen actually has a linguistic interpretation that you would like to be able to account for. So that all that structure is not accountable for in this model, because the only way you can put this algebraic structure together is with this non-commutative of algebra. The non-commutativity is not dependent on the specific form that I have of the product. Is inevitable because the trees are planar. So whatever way I have of defining them, I have to keep track of the order because of the planar structure. So it's whatever way I could cook up to produce a Hopf algebra here for using planar trees will necessarily have to be, non-commutative. Yes, there are some questions. Yes.
I have one. So, in the first tree there is one part where it gets split, and then that part ends up just being a single edge. Would you be able to like?
Yeah, that's right. So I have the things I'm allowing also trivial paths here in my decomposition.
And would you hypothetically be able to make as many trivial paths as you could?
That's right. So I could, that's right. I could make, like I could have a tree that has a lot of leaves here, right? So I would have to split my tree here into a large number of paths. And so I would be, at some point, I would be forced to introduce a number of trivial paths into it, because all the other ways in which I could split it into non-trivial paths are already used, right? And I don't reach the number of leaves that I have here. So I actually have to allow for several possible trivial paths to occur.
Right, and those trivial paths could essentially occur anywhere, is that right? Those trivial paths could occur anywhere, so for.
Yeah, that's right, it could occur anywhere, yeah, exactly. So you are summing over all these possibilities, as long as the number of terms that you produce is equal to the number of leaves that you have on the other side. Yeah. Yes.
Is there a more general way that I can think of the dual? Like, it's not a group anymore, but is it anything else that's interesting?
I mean, in what sense? Like,
I don't know. Usually when things become non-commutative, the duals become like one groups, or
yeah. Yeah, so I don't know. I mean, in a sense, okay. What I'm trying to argue here is that if you try to build the same kind of structure, the fact that so you are forced, like, by the fact that you only want trees and you want them to be planar, you're sort of forced into having your Hopf algebra structure have a more complicated structure. And so, and this is sort of inevitable, I mean, in the sense that, like, the non-commutativity is inevitable by the planar structures, and the fact that you have to graph trees together will necessarily, for example, tell me that the product will not be, so in the case of the disjoint union for forests, the product has a single output, right? There's only one way in which you can put two things together as disjoint union. But the moment that you have to do grafting, necessarily you're going to have several ways of doing that. So even if, okay, one could come up with some variant of this Loday-Ronco construction that is not quite the same, but it will inevitably have these two issues. Yeah, those are just inescapable, because you want the trees to be already planar, and you want them to just be trees. And so one way or another, you run into this kind of way. So I don't actually know if there's like some other variants that would work, which is not exactly the Loday-Ronco, but it would still have to have this type of structure. Right?
I think Edward's question is the dual a quantum?
Yeah, so the dual of algebra is kind of similar, right? I mean, because the product becomes the co-product and vice versa, right? So it's sort of similar that it's still coming from these decompositions of paths from roots to, so it's also not going to be commutative, so it's also not going to be functions on a group. It's whether it's function on something that's
Right, yeah, I guess my question was, it's gonna be functions on something more general, but maybe it's like an interpretation of that something more general. But
of
you're
that
saying
something more
from,
general. Yeah, so no, I mean, the quantum groups are these quasi Hopf algebras, right?
Right.
So where you kind of twist the co-associativity. And so this is not happening here. So the co-associativity works both for the algebra and as well. The thing is that that yeah, you lose the commutativity. So there's no scheme, no, which is dual to the algebra or the dual algebra, or whatever. So but okay, so what question that one can naturally ask at this point is, okay, this is kind of the way that you can assemble together into a Hopf algebra structure, these planar or binary rooted trees. What kind of relation does it have to these Hopf algebra trees that we have been using before, where you do these cuts on these admissible cuts, and where you actually necessarily have forests included and not just trees. Of course, you can make this itself non-commutative by assuming that the trees are planar and that the forests also are planar. So there's an ordering of the components, but still it would not involve just trees. It would also involve forests. And so this is what ultimately we do want to use, because the description of internal merge is coming from cutting a piece of a tree and pasting it back together. So we will have to somehow use these admissible cuts. So how do these exist in the context of these Loday-Ronco Hopf? So it turns out that there is a relation between this algebra of trees or forests with this kind of coproduct and the Loday-Ronco Hopf algebra. But again, it's kind of more complicated than what you would like to have, in the sense that, for example, to relate this to, you need to use not just binary trees, but also trees that are not necessarily binary. So there is a map that goes from this concrimer of algebras of rooted trees with the coproduct given by admissible cuts to the Loday-Ronco Hopf algebra. And it is a map that is actually a map of Hopf algebra and is compatible with the product and the coproduct and the antipode. The way it's constructed is a bit involved, but it's sort of you kind of build the map up so inductively on the size of your trees. So you start by taking this algebra of rooted trees, the concrimer of algebra of rooted trees has as unit the empty tree. And this Loday-Ronco Hopf algebra has as unit the single leaf tree. So you map the unit to the unit. So just at the moment, just vector space map, you map the unit to the unit. And then you map the single vertex tree in the case of the concrimer of algebra to the binary tree that has a single root and two leaves underneath. And then you build inductively the map, where you take a tree, you remove the root of the tree, so you cut it into a forest, and then you do this operation. So you have a map, which I'm going to describe in a moment, that assigns an element in the Loday-Ronco Hopf algebra to a forest. Now these are all smaller degree terms, so this is built inductively. So I know supposedly at this point know what this goes to. And then I have this tree and I attach it by this operation that attaches it to the left. Yeah. Okay. And what this is.
So you're using the same notation, it's not quotient. Right?
No, it's not. It's just this operation that takes it in, slides down that side and then attaches it at the bottom. And so for a forest, the way you do it is just repeatedly applying this other operation where you take the first three, you plug in the second one, you plug in and you pile them all up in this direction. Okay. So this is kind of looks kind of strange, but it's designed in such a way that it will be compatible with product and coproduct. So it's like the product on this side, on the concrimer, is just this joint union for forests. And it's non-commutative just because the planar structure, I'm taking care of the planar structure, but it's just a disjoint union of the components. And the coproduct is the one of the admissible cuts. And on this side, the product and coproduct are this more complicated operation with splitting along the paths of the tree. But it turns out that this kind of prescription for how you build this tree is exactly done right, so that it will preserve product and coproduct. So yeah, this is an example of how this goes. Like for example, this is where they respectively go from. Yes.
Yeah, I was just wondering, is this map specific to Loday-Ronco, or is it like a more general result that any Hopf algebra with some adjectives has a map from consequence?
No, I don't think so, because this is very much built by hand to actually match this product and coproduct. In fact, I'm not going to go through the proof that this really is a map of algebras, because it's a bit involved. It's in this paper. I've put it on the web page. You know, if you and also the old proof that this Loday-Ronco Hopf algebra has all the property. So it's but I mean the whole point that I make is exactly that there's a lot of ad hoc of this map to make the relation between these two. And that somehow you are here on the side that's, you know, in a sense, this side is pretty simple as a structure of Hopf algebra. And the Loday-Ronco side is a lot more complicated. And the map is correspondingly, you know, taking into account these additional complications that you have to have in order to, you know, have these grafting operations that always, you know, only deals with trees. Okay, so this is just a preliminary discussion about, you know, what happens with Hopf algebras when you're dealing with just with binary rooted trees. But now let's come back to this older formulation of minimalism that I talked about a while back. So here you have trees that are planar. Also, the information about the head structure of the tree is built into the labels that you attach to the internal vertices. Part of the information that goes in the labels of the internal vertices is exactly this information about where the head of the tree goes. So the head structure is taken care of, and also there are these other, you know, features, syntactic features, which tells you whether something is a noun phrase or a verb phrase, and something that also go into the labels that are attached to the vertices. And as I said, there are these other labels that tell you when something is calling for, you know, being connected to something with another feature, which are the theta rows part of the structure. And also there are, so these are these kind of selector features that will tell you that something has to combine with a structure of a certain type. And also there are these licensor, licensee, which are the ones that tells you when something can be moved somewhere else in the. So of course this first type, like these selectors, are the one that will tell you when external merge can be done. External merge is the one that's responsible for matching the theta roles. So that's what tells you what the domains of applicability of the external merge will be. And these ones that tell you when something can be moved in some other positions are the one that will tell you the domain of applicability of internal merge in this model. And so, and then of course, internal and external merge are defined respectively in terms of this grafting operation and in terms of this admissible cut. In this case, you just use these elementary admissible cuts so that everything is a tree, both the part that you are extracting and the part that remains, and not the higher ones. And the point is that now, these operations themselves are not directly related to the product of and co-product of the Hopf algebra, unlike in the new version where they are directly resulting from the co-product of the Hopf algebra. Here they're only related to these complicated relations between the two Hopf algebras, but you can still define these as operations on the Hopf algebras, like linear operations on the Hopf algebra. And with certain specific domains where that are required. And so, as I said, for external merge, each tree is itself labeled by the label that's carried by the head of the tree, and so you need to. You're able to apply an external merge to trees when the labels of the tree match up to this licensee symbol, which means that one of the two structures is calling for the structure of the other type to be combined to. This is kind of this coloring conditions of the colored operand in the formulation that I gave before. And so external merge is actually applying, and once you apply it, you modify the labels so that you remove the piece of the label is usually a string of different things that takes care of all the other possible, for example, theta roles that are associated to a particular element, and you just cancel the one that you have used to form the combined structure, and the remaining ones tell you which further operations are possible. And with internal merge, you use this other kind of labeling that tells you where something can be moved. And again, you can move something only if the label for the full tree that you have is the same, or has the same like initial part that takes care of movement, with the labels of the head of some substructure. And then you do the same merge as you have described before, but you can do it only when this matching of labels occurs. And so one thing that happens here is that, well, in the model, the more recent model that I described, you have this fact that you form a lot of structures that might not be compatible with labeling and so on, and those are filtered out afterwards. Here it looks like you're using this labeling to avoid the problem of conflicting labeling for the structure that you form. But the point is that even with this, you don't completely avoid that, because it could be that the remaining labels that you have are not necessarily matching, so you can end up with no labeling, but still can end up with structures that are not completely labeled. So it's not does not resolve that issue. So at the end, you still have to filter out some structures that are not anyway, even if you have domains. So it doesn't completely take care of that. So okay, these are like the examples, like I described some before, where you have this kind of label that tells you, for example, that if you have a predicate that is labeled as a verb, but it's calling for combining with two other that are labeled as a noun, and so on. So and then you have this kind of movement labels that tells you that you can move something from a position between these two positions like this if they are labeled with this possibility of movement. And again, these are all things that now become language dependent and not necessarily universal. So yeah, different grammars, you have different grammars that correspond to different languages. And of course, the fact that you have to check for these domains and matching labels means that you have a compounding problem when you start to iterate these operations. Say, if you have like a long chain of derivations to get a certain structure out of iterations of combination of external and internal merge, each time you have to do this domain checking. And so, in the end, when you have an iterated, you have to, so this adds to the computational complexity of the structure formation that we're doing. In fact, you can measure like how fast this the complexity of checking domains is growing, because if you have to do several of these operations and you have a certain string that is labeling the vertices, a certain string of syntactic features. So you can look at like the number of the syntactic features that are available, the number of possible strings that you can form, and you have a certain counting formula for what are all the possible planar rooted trees with those labelings, and then among these you have to check which ones have a good matching of labels. For example, if you want to do an internal merge, you want to check among all these possible trees which ones have matching pairs, so the labeling of the root has a corresponding labeling of one of the substructures that will allow you to do the merge. And so you can fix, say, what the label is at the root, and then look for arbitrary labels elsewhere, and among these check for domain consistency with whatever is the labeling that you have at the root. And so you have the necessary condition that defines the domain where you can apply it. In internal merge is where you have the matching between what you have at the root and the beginning of what you have at some other site that you want to use for movement. And so you can compute what is the dimension of the place that you're looking for that is matching the conditions. And this, you can see how it's growing, because if you have a certain, you fix a certain table, and then you are counting. So given what you have fixed at the root, what matters is the beginning, the beginning part that has to match. So you're looking at all the possible ways of having at least one of the other vertices that are labeled by the corresponding structure. So something that starts with the same sequence elsewhere. And so it's the same thing as saying that you're looking at all the assignments of labels that where not all of them are in the complement of this. Right? So it could be that you have more than one match possible, that's fine, but you have to have at least one. So it's like not all of them are not possible. And so the thing is that this counting to the number of these elements not in the complement is can be computed in this form inductively. And if you have repeated applications, so this is like for one application of this internal merge, and when you have a derivation that involves several such applications, then you can do the same thing. You can try to count. Then what at this point your root is going to have a certain string of labels, and you need to match a certain number of them with labels elsewhere. And then this again you can count, introduce some kind of counting function that does this, where you look at all the possible label assignments, where not all of them are in the complement of the set that you want when you want to find the match. And this is describable in terms of this kind of recursive formula where you add this term. So the point of this is just that you can see that the complexity of these little feature checking is growing very fast with the number of steps in your derivation. So this is one of the problems, with this implementation of this computational minimalism based on having all the structure formation after linearization and embodiment into one particular language, is that you have this explosion of computational difficulty in realizing the matching conditions. So this is one aspect of this older model that is not entirely satisfactory. And also, as I said, these internal and external merge, they correspond to fairly different kind of structures with respect to the Hopf algebra structure in this setting. So one thing, for example, is that so you have this operation that, say, internal merge. Let's just look at the internal merge first. You have this operation of internal merge. It has a certain domain on which is defined. And now, of course, you can ask how this domain behaves with respect to these operations of the Hopf algebra structure. Is it compatible, and to what extent is it compatible? And the one thing that's important here is that the information about the head function is built into the labeling of the trees. And because the applicability of the operation that you want depends on the head function, because you're checking labels at the head of the old tree and at the head of the substructure that you want to move. So you have to have these heads available, right, for this matching. And so if I form the product and the coproduct, in both cases here, let's what you do is you split your tree, right, and into structure, and in the case of the coproduct, you split it along these paths, and in the case of the product, you again split it and you plug it into the other tree. And when you split these trees along these paths, what happens to the head of the substructures depends on where your cut is going. They can all go into one side, or all go into the other side, or go one on one side and one on the other side. And so when you look at then what happens to this matching conditions that you need for whether the domain is preserved, it's going to depend on this. And so this means that the compatibility will require restricting your coproduct to a way that's compatible with these domains. And the way to do this is to restrict your coproduct to pairs of substructures that so cuts where the two parts have the property that either the head of the pieces that you want to use for movement and the head of the whole tree end up on the same side, or on one side or the other, and not one on one part, one piece on one or the other. Otherwise, you cannot do. They're no longer part of the same structure that you want to move. So you have to do some modification of the coproduct to account for these domains. And if you do this, then you get something which is compatible in the sense that if you apply the coproduct to the domain, you get something that is a co-ideal in the Hopf algebra. So a co-ideal means that it's something of this form. Like when you apply it to the domain, you get something where either one side or the other is still in the domain. This is the co-ideal condition for a Hopf algebra. And the same thing happens with the product. You have the same problem. You want to keep track of where the head of the old structure and the head of the piece that you want to use for the movement, whether they end up in the same component or not. And so this again requires a slight modification of the product where you only use those combinations of splitting that have this property. And this gives you once you make this modification of the product, it gives you that the domain is a right ideal for the algebra structure with this restriction on the product, but it's not a left ideal. And that's because like one tree ends up at the bottom and the other trees end up on top. And what depends on where the heads end up being is what happens at the leaves. So it's okay on one of, for what you can take care of that on the left side, which is the part that ends up at the leaves, but not on the right side, which is the part that ends up at the bottom. So you get something which is a right ideal and not a left ideal. This, of course, it's a non-commutative algebra, so you don't expect left ideals and right ideals to behave in the same way. So this is part of the fact of having to work with planar trees, that left ideals and right ideals will not be the same. And so the result is that you get this thing, which is a co-ideal and a right ideal. And not just this, but of course, every time you iterate this operation of internal merge, you have a new domain checking for the composite. And so you will get another, right ideal, co-ideal. And so you get a family of this. And you can form the quotient on one side where it is an ideal, and you get this right module coalgebras, which form a projective system. So the kind of structure that you get is the kind of algebraic structure that you get associated to internal merge in this old model is this family of projective system of right module coalgebras. So right module coalgebras are the best you can get close to a quotient of Hopf algebras in the case where the Hopf algebra is non-commutative. Because if you have a commutative Hopf algebra, a quotient is a Hopf ideal. So it's an ideal and a co-ideal. But in a non-commutative Hopf algebra, you would need something that is both a left and a right ideal for the product and a co-ideal for the co-product. But usually, you have very few left and right ideals. So in order to have quotient structures that are interesting, even when you have very few ideal co-ideals, people often use this notion of right module coalgebra as a substitute for a quotient of Hopf algebras. So it's the analog of the quotient structure in this. So this is what these internal merge operations define at the algebraic level. And the external merge, on the other hand, is now something different, because the external merge is using two trees, but you don't have forests in your Hopf algebras as object. You only have trees. So you have to think of what is this structure, this binary operation that involves two separate objects in the Hopf algebra at once. So it's not a linear map on the Hopf algebra itself, because you don't have those as elements of the basis of your Hopf algebra. So it's a kind of quadratic structure on your Hopf algebra. It's kind of quadratic form on your Hopf algebra. And in fact, there is a notion. This is actually kind of a very fairly broad subject, which is called operated algebras. It's also goes under the name of Rota's operated algebra program. It's a kind of way of classifying algebras together with some kind of linear operators that satisfy some polynomial constraints on the algebra. And these include various things, Rota-Baxter operations, which I will be talking about a lot in the next lectures, Leibniz rules, brackets, various kind of quadratic operations that you can introduce. And basically it's a way of trying to classify various kind of structures of polynomial type structures on algebras. And one particular case in these operated algebras setting is called, lambda, well, I'm actually using this notation lambda v because, our trees are pointing down. It's usually written as v again, because usually the trees are written, with the root at the bottom. So, not a fact, but let me just call them lambda omega algebras. So this is the general way these are defined, is that this is an algebra. And it has a binary operation on it, which can come with in several flavors with given labels, like this grafting of trees that when you have labeled vertices in our case. And it satisfies an identity with respect to the product. So it has to distribute over the product in this way where you can, whenever each element can be split according to this operation. So this is exactly like in the planar trees, like you can separate out the left and the right part below the root. So it means that every non-trivial element has a decomposition like this. And we know by the construction of the product in the Loday-Ronco of algebra is exactly designed so that this identity holds. So this grafting operation, which defines the external merge, is the operation that exactly gives this type of structure to the algebra. And it's if your algebra is not just an algebra, but is a Hopf algebra, as in the case of the Loday-Ronco Hopf algebra, then in this setting, one also requires that this grafting operation here satisfies the cocycle condition, which is this identity here with respect to, so this is how it behaves with respect to the product. And here is how it behaves with respect to the co-product. So the co-product applied to this merge has to satisfy this identity here, where this is the part that flips the two middle terms of this tensor product. And indeed, again, the Loday-Ronco co-product is built with respect to this grafting of trees exactly in such a way that this is satisfied. And the reason why this is called a cocycle is because it defines a cocycle in the Hochschild homology of the Hopf algebra. So it is related to the natural kind of homology theory that you can define for algebras and Hopf algebras. So this is what the external merge is in this setting. It is this structure on a Hopf algebra. So okay, I mean this is kind of an interesting algebraic structure, in itself, and it again shows that there's several nice compatibilities, between this operation and the Hopf algebra structure, but it's a lot more involved than the way that the merge is defined if one takes as Hopf algebra point of view the one of the forest, of the binary root of forest with a coproduct given by the cuts. And so in this sense, seen from this algebraic perspective, it kind of shows that there's a significant conceptual simplification in replacing this older model with the newer one that I've been talking about before. And so, I mean, one reason why this, doing this part of this comparison of structures with this older version of minimalism is quite, in part, okay, I'm sort of trying to justify my own issue with this story, because in a long time ago when I was at MIT, when I was working at MIT, and this older version of minimalism was being developed at that time. And Noam was teaching his linguistics class with this version of minimalism. I actually sat in that class, and all the time I was thinking, well, this kind of reminds me of something, and I couldn't quite pin down what it was. And then, fast forward like 25 years, and I finally got it. But to my disclaimer, as you can see, the older version of digging out this Hopf algebra, the fact that the Hopf algebra point of view is the natural way of thinking about these things from this older version of minimalism is a lot less evident than it is in the newer version. So it's not just that it was much dumber at the time, but maybe I was, but I'm just trying to claim that I wasn't. Okay, so let me see what we're doing. Okay, I will almost finish the time for today, but I can just say a couple of words about what I want to discuss next. Okay, so the next things that I want to talk about for a while is this model of the interface between syntax and semantics. And in a sense, before I start to build that model, I want to give a little bit of a comparison between the kind of structures that I've been describing so far and where the same kind of structure occurs in theoretical physics. And the reason for that is because, of course, the way that we've been thinking about this is very much modeled on what was already known in theoretical physics that has a very similar kind of structure. And somehow, of course, this is like a general philosophy that when you see the same kind of structure occur in different settings, it's a good idea to try to wrap up whatever that has worked in one particular setting and try to see how much of that can be transferred to the new setting where you encounter the same structure. Right? This is one of the most successful ways of trying to do something. Capitalize on what you already know it works. It works somewhere, it might work somewhere else. That's as simple a philosophical principle as there can be one. And so I'm trying to, I'll do it next time, but I want to try to, very quickly, this is not a class about quantum field theory, so I'm not gonna be going into details in describing how renormalization in quantum field theory works. But I want to just get a very heuristic kind of description of why the same kind of structures that we have been discussing from the beginning of this class have a role in almost exactly the same form in this setting in theoretical physics. And in a sense, the main point is what is the main things that this algebraic structure do for you in the setting of theoretical physics. And the main point that I want to focus on is that in perturbative quantum field theory, these kind of algebra structures are responsible for organizing a certain procedure, which is renormalization in quantum field theory. So as I will say next time, one of the main problems is that when you try to perturbatively compute the expectation values of observables in quantum field theory, you run into contributions at various orders in your perturbative expansions that are labeled by graphs. So there is a combinatorial, a generative process of combinatorial structures associated to a particular given quantum field theory. And each of these combinatorial objects comes with a certain calculation attached to it of an integral in the momentum variable. That is the contribution of this term to your overall computation that you're trying to carry out. And the problem is that a lot of these computations are meaningless. And the reason why they're meaningless is that because most of these integrals diverge. And so at the end of the day, you want a meaningful physical value. And so you have to somehow throw away all these infinities, or rather, renormalize them. So extract some finite values from all these divergent integrals. And you have to do that in a way that is compatible with substructures in the sense that you go order by order, which means that you are encountering bigger and bigger graphs as you continue. And as you encounter bigger graph, you're going to encounter smaller graphs as its subgraphs. So things that you have already taken care of in this renormalization procedure. And so how you renormalize the bigger graph has to take into account how you have already renormalized the smaller graphs that it contains. So there has to be some kind of recursive compatibility condition. And so this was a very well-known problem in the history of quantum field theory. And there was like explicit formula for how to do that. Bogolyubov, Parashuk, Zimmerman is the BPHZ, the main name of the game for this kind of formula. And the point is that it's if you look at the early literature on quantum field theory, this kind of look like black magic. You do this, you do that, you combine these things, and it works, and it does. But why? So the key thing in this is that what you are writing there in this formula is a particular procedure which is called Birkhoff factorization and which is associated to a Hopf algebra structure. And so the Hopf algebra structure is exactly what organizes the checking of consistencies across substructures. And now, I mean, you can see why it's easy to think that this, if you have this other setting in linguistics where the same of algebra structures comes up, that this is a natural way where to look for a model for how we parse for syntactic meaningfulness in a structure, because parsing for semantics is also a way of trying to extract meaningful values, meaningful interpretation from a structure in a way that has to be consistent with the parsing of substructures. You sort of build your parsing again bottom up, so it's like going into the terms of your perturbative expansion toward larger and larger graphs. And the parsing of the smaller structures has to be combined in a consistent way for the overall structure to be parsable. And so, it's kind of natural to see that if you have an algorithmic way that takes care of exactly this kind of problem in the setting of theoretical physics, the same kind of approach is likely to take care of the same kind of problem in this other setting. So what I'm going to do next time is, I'm going to just give a little overview of how these Hopf algebra structures and this renormalization problem work in the physics setting, and then I'll start with building the linguistic model for the syntax semantic interface, and we'll see what matches what with respect to what was known before in the physics setting. Okay, right.